the square today. This is another option for solving a quadratic. So far we've looked at graphing a quadratic, how we can find the x-intercepts. We've looked at factoring a quadratic. We've looked at using square root property. There's one other one after this we're going to look at the quadratic formula. But completing the square is one of the two methods by which we can take any of our quadratics and solve for our variables. What the goal of completing the square is, we want to take a trinomial that is not in perfect square trinomial form. We want to manipulate it to get it into perfect square trinomial form and then be able to rewrite it into a binomial squared or a factor form. So these are our two goals here. Take something and put it into the expanded form, which then we can put into the factor form, and then use the square root property. So that's hopefully what we're going to be able to do by the time we're done with this. This is just a little visual of completing the square and the process by which we do it. We focus on the part of the trinomial that includes the ax squared and bx piece. And to complete the square of that binomial, x squared plus bx, we would have to add to it this b over 2 squared. And that would become our new c value in our standard form. So we're going to check the field of SSD. All right, so here we see a little schematic. The blue square being x squared, and then bx has a side length of b with a height, we'll say, of x. And here's the process of cutting that green rectangle in half and then placing this portion of that rectangle here underneath the x squared, and then having a gap that would be filled by this quantity b over 2 squared. So the visual, that's what's happening. Let's actually take a look at how some problems can be solved through this process. So with problem A, x squared plus 20x plus 100 equals 81. What we would normally have done at this point is we would have tried to make one side of this equation 0, and then from that hopefully be able to factor. Well, we're going to actually show this process of where does this b over 2 squared come in with this problem. If you look at the left side of the equal sign, x squared plus 20x plus 100, we have our ax squared bx part of the problem. And if I took the b value and I divided it in 2 and squared it, I would get 20 divided by 2, which is squared, which is 10 squared, which equals 100. And that is what is at the end of this trinomial. So what that tells me is that x squared plus 20x plus 100 is already in the completing the square form that I would want, so that I can do this. Factor x plus 20x plus 100, and I would get x plus 10 squared. So there's the binomial square that we were after, so that I can use the square root property. I still have equal 81 here. And at this point, we can square root both sides to get x plus 10 is equal to plus or minus 9. And that means x would equal positive 9 minus 10, or negative 9 minus 10. X equal negative 1 or negative 19. Now, had I not done any completing the square and simply moved that 81 to the other side, and then I factored this, and then zero product property, I would have found the same solutions that we found when it was set up in a completing the square fashion. All right, so let's actually talk about the b over 2 squared and why that's useful to us. What is its purpose? We'll do that with these problems. Here it's asking us to find this value of c so that we make a perfect square trinomial. Again, perfect square trinomial, x squared plus 2 use variables. A squared plus 2ab plus b squared. That would be our perfect square trinomial. And again, this c value is found by doing that. Taking whatever the b term is, half of the b term, squaring it would produce this value of c. And by me finding these values of c in this way, I am able to then take that trinomial and make it a perfect square trinomial, where it may not have been that before. So if we do that on A, I think about making c equal to my b over 2, and then squaring it, I'd have 26 over 2, or 13 squared, or 169. So x squared plus 26x plus 169 is factorable into x plus 13, x plus 13, or x plus 13 squared. And that's our goal, is to get us into that format so we can write a binomial square. Let's try it here with b. Again, taking my b term and half of it, and then rewriting it as a perfect square trinomial, and then recognizing that this perfect square trinomial can factor, I would get x plus 6 squared. Now, I want you to pay attention to how we derive the factor form from these, because there's a very quick way of coming up with what this binomial squared looks like. You'll notice in the above problem, this one here, that when we put it into a binomial squared form, this term, this number here, was always half of my middle term. So we see it again here. We have 6, which is half of my middle term. So when I write these binomial squares, I'm able to do that. I'm able to just simply use the b value, cut it in half, and that will become the second term of my binomial here. And I always am also paying attention to the signs. So if it was a positive b, I got a positive binomial squared. If it was a negative b, as in this case, we have a negative 24 now. So now if I took half of my b and squared it, I still get a positive value. So you're always going to get c that's positive every single time. But then if I go and write the factored form of this, and I do half of my b, I get x minus 12 squared. If I were to FOIL that out, I would get x squared minus 24x plus 144. So again, that's what I would get if I were to factor. All right, so the cool little trick. C is always b over 2 squared. The binomial form, the second value of the binomial, is always half of b. So then here is the process of completing the square in which we have an a value equal to 1. We're going to take a look at what happens if you have an a value other than 1. We basically will add one step prior to step number 1 here on this setup. So here we're walking ourselves through each of the steps. There are 5 steps for completing the square. We looked at the original problem, x squared minus 10x plus 1 equals 0. We know that I can't find factors of 1 that can add up to negative 10 in the middle. So that is unfactorable as it currently sits. So what we're going to do is we're going to focus again on the ax squared bx part of the problem. So we're looking at this part of the And we're seeing what would I have to add to that as a constant number so that it becomes a perfect square trinomial. And in order for me to do that, I have to kick that 1 out onto the other side of the equation. So step 1 for this process involves moving that constant c, which right now is a 1, over to the right-hand side of the equation. And that's what happened in that process right there. Just move the 1 over to the right side. And step 2 would involve us taking the x squared minus 10x, recognizing that I've got my b term right there is 10. I take half of that b term, and then I square it, and I add that value to both sides. So that's what happened. We took half of our 10, and we got 5, and we squared that, and that's what shows up on both sides of our equation. Step number 3 would then be to write the left side as a binomial squared. And we use our little trick. Half of negative 10 would be negative 5. And that's what's showing up in the parentheses right here in the binomial. Square it. And then negative 1 plus 25 on the right-hand side became a 24. Step 4, we take the square root of both sides. Once you get that isolated squared item, squared binomial, now you're ready to undo it by the square root property. And that's what happens. We square root both sides, and remembering that when I do that, I'm going to get a plus or minus on the right-hand side. So x minus 5 shows up and equal to positive, negative, plus, minus the square root of 24. And then the last step would simply be solve for the x. So we would add that 5 to the other side and end up with 5 plus or minus 2 root 6. So what that means is we have two answers. We have one that says 5 plus 2 root 6. And then we also have one that says 5 minus 2 root 6. So this plus minus thing indicates two solutions, as long as we have something underneath our radical there or something on the right-hand side. So let's try that with this problem now. We're going to complete the square on this one. So step 1 would say move the constant 12 to the other side. Step 2 would say take half of our b term, square it, and add that to both sides of the equation. So I'm taking half of negative 8, and I'm squaring it, getting a 16. And I'm adding that to both sides of my equation. Step 3 would then take the x squared minus 8x plus 16, the left side of the portion of the problem, and make it a binomial squared. And it always breaks down into x. Whatever the sign of b is, you go in here, and whatever half of b is, you go in that spot. Combine my like terms on the right side, add those numbers, and I get a 4. The next step of that process would be then to take the square root of both of these sides. Doing so, we would get x minus 4 equals plus or minus 2. And then lastly, we would have 4 plus 2, or 4 minus 2, with answers of 6 or 2. And those would be the solutions to that quadratic, which are also your zeros, because we have the polynomial value equal to 0. So we found x-intercepts right here. All right, we're going to try this one. So if you want to work on it on your own, practice it, pause right now, and then come back and check the answers. X squared plus 6x equals 10. X squared plus 6x plus half of 6 squared is 9. And that goes to both sides. So we did our binomial squared on the left. We ended up with a 19 over there on the right-hand side. We square rooted both sides. Plus or minus the square root of 19. That's okay. I'm just going to have a radical in my answer. Move the 3, and we get negative 3 plus or minus the square root of 19. All right, it's a cool thing, completing the square process. It's very helpful for us. Now we see what is it going to do when that a is not a 1. So we have a leading coefficient this time, something bigger than 1 or smaller than 1. You can have 1/2 in here as well. We add this new step. And this step 1 and the previous step 1, when the a was equal to 1, that process, these are actually interchangeable. I could do this part first where I divide all of my terms out. I divide an a from all of my terms. Or I could move the constant first, the 150 to the other side, and then divide out. It doesn't matter. You're going to get the same solution. We're going to go ahead and just stick with the plan here of following this process. So I would say a is 3. I'm going to divide the entire equation by 3. And I get now x squared minus 12x plus 50 is equal to 0. At this point, the problem becomes just like our last 2 or 3 examples of completing the square. Our a is now a 1. We would move the constant to the other side. We would figure out what half of our b was and add that to both sides. We would complete write the binomial square of my perfect square trinomial and simplify the right-hand side. Then I would take my square root, get an imaginary here, plus or minus I root 14, and then 6 plus or minus I root 14 would be my answer. Now, what's unique about this answer is those are imaginaries. They're not real solutions. So we have no real solutions, and that means we have no x-intercepts. We have no real solutions when the polynomial is equal to 0. So therefore, no zeros, which are our x-intercepts. So what that tells me about this graph is that it's a parabola that's either starting above the x-axis and opening up, or it is starting below the x-axis and opening down. So it looks something like this. Maybe it looks like that, or perhaps it looks like this. No x-intercepts. So understanding and interpreting the answers that we're finding, not just going through the motions of coming up with the answer, but understanding what they can tell us is something I hope that we develop, or you guys develop. All right, you can try this one again, and I will work it out, and you can come back and check. We're seeing examples where these b values are even, which is really nice because when I cut it in half, I have a number I can work with. Sometimes, though, our b values aren't even. So in that process, what's going to happen is you end up with b over 2 that's just fraction. And it's still doable. You just have to remember when you square a fraction, you're squaring the numerator and the denominator side. So don't worry if I end up with a b over 2 that's fractional. It's still going to be an answer that you can work with. All right, I'm going to do this one again just to this one up just so we can see how a fractional b over 2, maybe we change this to become a, well, let's just make it a 15. Why not? I divide everything by 4 still. I get x squared plus 15 over 4x minus a 15 equals 0. So now I got this b over 2 that's a fraction. We still do our, let's take half of b and square it. So let's review that. If our b is equal to 15 over 4, and we're looking for b over 2, that means we're taking 15 over 4 divided by 2. And that's a situation where we keep the numerator and we multiply by the reciprocal. This becomes 15 over 8. And then if we have to square our b over 2, then this becomes 225 over 64. So there's our b over 2 squared. So it's a little more challenging here. So we get x squared plus 15 over 4x plus 225 over 64 equals 15 plus 225 over 64. And then our binomial squared would simply be what our b over 2 was. So remember, when we did our b over 2, that's what this number was. 15 over 8. So I'd write this as plus 15 over 8, quantity squared is equal to, and then I'd have to figure out 64 and 15, because we're going to just change that so everything is a common denominator. So 64 times 15, 960. So I'm changing this to become a denominator that has a 64 in it. So this is some good fraction practice. And then 960 and 225 becomes 1185. And here we can square root both sides. Square root of 1185 over 64. Square root of 64 is an 8. And 1185, probably we could simplify radical that, but for the sake of just time here, I'm going to just leave it. So I move that negative 15/8, I get plus or minus the square root of 1185 all over 8. And that would have been my solution. So it's the same process, it's just we're working with fractions, and I know some of you guys don't like fractions, but fractions are your friend. So there we go. Just tweaking that problem to put ourselves with a b that's odd. Given the area of a triangle, what is the value of x? All right, so we have this triangle, and we have been given the area as 144 units squared. We know that the height of the triangle is 2x, and the base of the triangle is x plus 10. Now, I should have probably put this in here. How I know that those are the heights and the base are those are perpendicular to one another. And this line that comes from a vertex down to the base that connects perpendicularly is called an altitude, another name for height. So if that's the case, and I know that the area of a triangle is equal to base times height divided by 2, I have a base that happens to have a variable in it. I also know the area is 144, so I have an x plus 10 as my base. My height is 2x, and we're going to take all of that and divide by 2. What would I do here? Get that 2 out of there, so multiply both sides, or the entire equation, by 2. We get 288 is equal to, I'm going to just change the order here, 2x times x plus 10. We'll go ahead and distribute that 288 equals 2x squared plus 20x. And then I could, interpret whether or not that makes sense. So we found that answer, but do they make sense? Can I actually have a negative length for my triangle? Even though I get a negative 18 there, 2 times negative 18 is negative 36, negative 18 plus 2 is negative 8. So that really doesn't make sense. Even though I found the answer, you have to apply it to the given situation. And in this case, we're applying it to a length of some object. So I can't include that negative value. So we're not going to use that one. And we'll just use 8. So our answer would have been C on that. So you have to interpret based on what it is that you are trying to find. All right, let's look at the, it's kind of a, I don't know why that one's here. Get rid of that guy. All right. We have been working with our three quadratic forms: standard form, vertex form, intercept form. And we have already worked with the process of converting intercept form and vertex form into standard. We have not, though, gone the other way. And that's what the process of completing the square can help us do. We're going to take ourselves out of a standard form and put ourselves into a vertex form. Might be helpful for a couple different reasons. One, it's quick to see our vertex for sure. But let's see what the process looks like for this. The completing the square process, we tweak it just a little bit. One of the things that we're going to do is we're going to leave our C value, our 7. We're going to leave that actually on the right side of our equation. And I have now, instead of a 0 equals, where I would be factoring or trying to find the values of x, I have a y equals. So we're just changing the form of the equation, but doing that through the process of completing the square. So step 1 in this process, we group the ax squared and bx portion of the problem. So we see in red, the 2x squared minus 8x is our ax squared plus bx portion, and we factor out the a value. Now that a value is the leading term in front of the x squared. Now that a value may or may not go in as a factor of b. It might not divide nicely into b, and if it doesn't, that's okay. We can still factor it out. So what I'm saying is if we had something like this as our ax squared bx situation, and I said, I'm going to factor a 2 out of that. Even though 2 doesn't go into a 9, you can still pull it out. And then you just end up with a 9 halves that results. After I factor out a 2 from a 9, I have a 9 halves. Think about dividing 9 by 2, you get 4 1/2. That's where the 9 halves comes from. All right, so we did that here in step 1. We grouped and we pulled out that a, 2. Now that a becomes the a in my vertex form. Step 2, we take half of our b value, and in this case, in this problem, our b value is this -4 value here. We square it, and we add that to make our perfect square trinomial. So this process isn't any different. We took half of -4, we squared it, and that is where our 4 came from. Now what's different though is before when we were doing this, when we took half and squared and added it to both sides, we never had this a hanging out in front of our parentheses, because that was always a 1. So now what's different is we need to account for that a and realize that what I've done is on the right-hand side of the equation, I've actually added 2 times 4, or I've added 8 to the right-hand side of the equation, which means if I want to balance my equation, I must also add 2 times 4, or 8, on the left-hand side where the y is. It's just a matter of balancing. Step 3 then would take our perfect square trinomial and write it as a binomial squared. That's what's happening here. So we've taken the x squared minus 4x plus 4, we've we put ourselves into vertex form. So we want to move that 8 to the other side by subtracting, and end up with a vertex form. So there's using the completing the square process to help yourself get into the vertex form. Very handy. Just got to keep yourself. The tricky part again is this step number 2, where I have to remember I have to multiply the a by whatever my b over 2 squared value is, and make sure I put that on both sides. So let's try one, or you guys can try one. Again, you can maybe pause and work through your steps. Go back and check the notes and work through your steps. I'm actually gonna swap these guys. I'm gonna do one that has a b value or an a value other than 1. Maybe we'll just stop on this. So I would first consider my group that I'm working with. I would then, from that group, factor out the lead term. At this point, I'm going to complete the square on the x squared plus 6x portion of the problem. X squared plus 6x, half of 6 and square it. 3 squared is 9. Right? I actually didn't add 9 to the right-hand side. I added the product of 9, 3, or 27. So that means over here, I need to add a 27. Now we're ready to, on the perfect square trinomial, put it into our binomial squared form. So x plus 3 squared minus 13. And then simply kick that 27 back over to the right-hand side by subtraction. And I get negative 40. And now I'm in vertex. All right, let's use this last example problem to finish our lesson out. I'm not going to do that B problem just because it has an A that's a 1. So, all right, the height h of an object t seconds after it's thrown is given by this function. So now this is projectile motion type of problem. We're throwing something. And we've seen this equation before, something that looks very similar to it. We have this h of t equals negative 16t squared plus 64t plus 50. And before, when we were doing these problems, we were told that in these projectile motion problems, it was a v sub ot and an h sub o, where v sub o was your initial vertical velocity and h sub o was your initial height. All right, and we've been working through these kind of application problems all through this chapter. We need to get squared away that maximum and minimums occur at a vertex. So anytime I'm asked about maximum and minimums, I need to go find that. We now know how to find the vertex in either standard form, with using x equal negative b over 2a, or vertex form, the equation tells me the vertex, or intercept form, where I can use axis of symmetry x equals p plus q over 2, and then plugging that back in and finding 1. So if I can make something in vertex form, it's very easy for me to see the answers to problems that involve heights of objects, what are their maximums, what are their minimums. And that's what we're going to do on this problem. We're going to complete the square on this h of t equals negative 16t squared plus 64t plus 50. All right, first thing we're going to do is we're going to pull out that lead term. Factoring out a negative 16 from a positive 64, we get a negative 4t. And then we go ahead and do our half of b. In this case, it's a negative 4. Square it, get a 4. I recognize that I have, actually, on the right-hand side, I've added a negative 64 there. So we're going to make sure that we balance that on the left-hand side by taking my h of t and subtracting 64 as well. Then I'm going to go ahead x, or in this case the t part of my vertex. I add 64 to 50, and I get 114. There's the y part of the vertex. So my vertex, which again is hk, is equal to 2, 114. Now, this information, we got to interpret it. What is this? This is the time it takes to get to the maximum. Or minimum if we're looking for that. And this number is the maximum height. The question asks you for what is the maximum height of the object. And we're working in feet here. It doesn't tell us this other than the fact that I know I'm working with seconds. I guess we could interpret it as either unit meters or feet. We'll go ahead and just leave it. So the max is 114. We'll just write units. Don't know if we're talking about feet or units, feet or meters. So there's your answers. Remember, it's just a part of the vertex that answers the question of what the max or minimum is. The other part answers the question of when it occurs. So there we go, completing the square. Very useful